Okay, let's look at the chemical formula and the mole in chapter 2. As you saw, we have lots of chemical symbols in the periodic table. However, we don't just deal with atoms, individual atoms all the time, we deal with molecules. So we have to have a way to write certain chemical formulas to describe the compounds that we make out of individual atoms. And there are several ways that we can do that. Let's take an example. If we take glucose, for example, here are 3 different ways of depicting glucose. The first way that we use is called the molecular formula. In a molecular formula, every atom is listed, and it's listed by its symbol. And then we add these subscripts by each atom that tells us how many of these atoms are present in the molecule. If the subscript is 1, we don't write it. We just assume that it is 1. So in one molecule of glucose, I have 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. So I have 6 times as many atoms of carbon that I do 1 molecule of glucose, because I have 6 carbons for 1 molecule. I have 12 times as many hydrogens as I do in a molecule of glucose, because 1 molecule gives me 12 hydrogen atoms. 1 molecule of glucose has 6, so 6 times as many oxygen atoms. If I had 2 molecules of glucose, I would have 6 times 2 carbon atoms, 12 times 2 hydrogen atoms, 6 times 2 oxygen atoms, etc., etc. These subscripts, then, they tell us how many of each element there are in a molecule. And they're written to the lower right-hand corner of each symbol. So the 6 here belongs to the carbon, not to the hydrogen. The 12 belongs to the hydrogen, not to the oxygen, and the 6 belongs to the oxygen. That is the molecular formula. The empirical formula is similar to the molecular formula in that it shows us every element by its symbol, but it shows us the lowest ratio to each other. For example, from this molecular formula, if I divide everything by 6, this is the lowest ratio that I can get. If I divide everything by 6, I get 6 divided by 6, 1 carbon, 12 divided by 6, 2, and then 6 divided by 6 gives me 1. I cannot reduce this any longer. This is the lowest ratio of each other, of the elements to each other, that I can get for this particular molecule. And when we do that, this is called the empirical formula. It does not always represent the molecule directly as a whole, but it's just an easier way to denote the ratios of each atom to each other. Note that you can have compounds that have the same empirical formula, but they might have different molecular formulas because it depends on what the ratios are. For example, if I had a molecule that had, let's see, instead of 6 here, I would have 7, 14, and 7. That would still give me CH2O, but it would be C7H14O7 instead of C6H12O6, which would be a slightly different molecule. So with that said, we can have compounds that have the same empirical formula, but they will differ from the molecular formula because it depends on what they were reduced from. Okay, here we reduced by 6 to get this empirical formula. I can reduce by 3 to get, for a different molecule, I can reduce by 3 to get this formula, etc., etc. So empirical formula doesn't really represent the reality of the molecule as a whole. And that's why we have the molecular formula. Then the last way of representing a molecule is the structural formula. Molecular formulas are all good because it tells us what types of element are involved and how many of each. However, it doesn't really tell us how these are arranged in a molecule. I don't know who is bonded to what. By just looking at this simple notation here, I cannot tell which molecules are connected to what. And that is what the structural formula is for. Here is the depiction of glucose. At every corner, every intersection here, there's a carbon. We don't write them all, but there's supposed to be a carbon here, or there is, it's just assumed so. So at every point where we have lines that intersect with each other, there's a carbon. So there's a carbon here, 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 and here. So by just looking at this, I can't tell how this molecule looks like in three-dimensional shape. But if I look at this molecule, I see that, oh, this is called a six-membered ring because it's made up of six atoms in a ring. I have 5 carbons that are bonded to 1 oxygen and form the plane of that ring. And then I have a carbon sticking up here with a couple of hydrogens, an OH group, and then I have OH groups all over the place here. 1 is sticking up and 3 are sticking down. So this tells me, once again, it tells me how the molecules are connected to each other. And even this is a full structural formula because I'm missing a few hydrogens. I should have 1 here, 1 here, 1 here, and 1 here, and even 1 here. But it gets a little too crowded, so we assume that there's a hydrogen there. Anyway, that's the difference between the structural formula and the molecular formula. If we are just doing calculations or we're writing out a chemical reaction, we don't necessarily need to know the structural formula. But if I am looking to see where a compound might bond with this glucose, where it might react, it might be helpful for me to know the structure and how it looks in three-dimensional shape. All 3 of these are important and they have their place, they have their value. We use them interchangeably, we use them all the time in chemistry depending on what exactly we need. And that's why we've developed all 3 of them. Here's another example of the same idea that we can have molecular formulas that are the same, or even empirical formulas that are the same, but we have different compounds. Here, for this example, we have 3 compounds that have the same molecular formula and even the same empirical formula, but their three-dimensional shape is different. These compounds are called isomers. They have the same molecular formula, but their atoms are connected in a different order in three-dimensional shape, and they will be different compounds. It is important. It's not necessarily intuitive to think of atoms connected in a different order making a difference in a molecule, but they do, and therefore they will make a different compound that has slightly different properties. And that's obviously important, especially in biological chemistry when we look at these sugars and in the body and how they react with other compounds, how they're broken down, etc., etc. One might work differently than another because that one switch in three-dimensional shape is enough to change the properties of the compound. So isomers, the definition of isomers are they're compounds that have the same molecular formula, meaning they have the same type of atoms, the same ratios, the same number of each atom, the same ratios between each atom, but these atoms are connected three-dimensionally in a different order. Here's these examples. I have glucose, which we just saw from the previous slide. Okay, here's my molecule of glucose. It is very similar to galactose. The only difference is in this position number 4 here, this carbon 4, where glucose has the hydrogen up here and the OH down here, whereas Galactose has the opposite order, where the OH is now where the hydrogen was, and these two are flipped from the glucose. So you might think that that little bit of a switch is not a big deal, but it is enough to make the chemistry of these two compounds different. And therefore, these are isomers, so they're not exactly the same compound, even though they have the same molecular formula and the same empirical formula. Now let's look at the last one. This also has the same molecular formula. It has 6 carbons, 1, 2, 3, 4, 5, 6. It has 1, 2, 3, 4, 5, 6 oxygens, and if I counted the hydrogen, there'll be 12. So exactly the same as glucose and galactose. But look at the shape of this molecule. It has what we call a 5-membered ring, meaning a five atoms to form this ring, a pentagon, instead of a hexagon. I have one less carbon in this ring, but I have one more carbon sticking up here. So instead of this carbon being in the ring, it is now sticking up here, and the oxygen, instead of bonding here, is bonded to this carbon directly. This is a completely different compound. Once again, all these 3 molecules are isomers because they're compounds that share a molecular formula, but their atoms are connected differently in 3-dimensional space. This is also important to remember. Now, we've talked about molecules, and we've talked about how the atoms combine to form molecules, and how we write molecular formulas to describe the compounds, etc., etc. And we also talked about the mass of the atom and how we calculate the average atomic mass. However, we have to introduce another concept, the concept of the mole, because we don't really deal with single atoms, single isotopes. We have to deal in a much larger scale because we're limited in the microscopic scale, obviously, how small we can go. We cannot measure individual atoms at a time. That's not possible for us to do. We therefore need to look at a larger scale, and let's talk about the mole. First of all, let's look at this molecule of H2S. If I were to just look at the masses of each element in this molecule, I would find that the molecule is made up approximately 94% of its mass comes from the sulfur, and only about 6% comes from the hydrogen. Well, if you just looked at the formula like this, you wouldn't guess that. You would say, well, I have twice as many hydrogens as I have sulfur, so the percentage of the hydrogen should be larger than the sulfur. Well, that's not the case. Why? Because sulfur weighs a lot more than hydrogen. So we have to have a way to actually, if we cannot just look at the masses and make an assumption about the formula, the molecular formula of the compound, we have to introduce another way of measuring individual masses and comparing them when it comes to the molecules. And not only that, but then we have to look at how many grams do we have at macroscopically. We have to go from the microscopic scale of one molecule of H2S to the large scale in the laboratory when I weigh enough grams of this molecule, and I have to know how many do I have. For that particular purpose, we relate these ideas to through the idea of the mole. So we relate the atomic mass to the larger quantities of grams, for example, in the laboratory scale, through the mole. So what is the mole? A mole is equal to, it's just a unit number, okay? It's a measuring, it's a unit of measurement. 1 mole is defined, it's equal to 6.022 times 10 to the 23rd atoms or molecules or formula units, meaning ions or whatever. This is also called Avogadro's number. Now, think of the mole. I know this is kind of a large number to think about, but because we're converting from a small scale, like one atom, to a large scale, to grams. So there's many, many atoms that are included in a mass in grams. If I look at a mole as just a measurement, such as a dozen, for example, if we know that 1 dozen is equal to 12. So if I say I have a dozen molecules, that means I have 12 molecules. If I have 1 mole of molecules, that means I have 6.022 times 10 to the 23rd. It's the same idea, it's just a different number. So if I have 1 dozen, I have 12. If I have 1 mole, I have 6.022 times 10 to the 23rd. If I have 3 dozen, I know to figure out 3 dozen by multiplying 3 times 12 because I know 1 dozen equals to 12. If I have 3 moles, I will know to calculate it by 3 times 6.022 times 10 to the 23rd because I know that 1 mole is equal to that much. So think of the mole as just a unit for converting from a small scale to a very large scale, a mass in grams. Now, we also define the mole as the amount of a substance that contains as many particles, such as atoms, molecules, etc., as there are atoms in exactly 12 grams of carbon-12. So if I were to weigh exactly 12 grams of carbon-12, that would be the definition of a mole, and it would contain 6.022 times 10 to the 23rd atoms of carbon-12. This is my definition, is exact, and therefore so basically it's just like the AMU that I defined earlier. I defined the 1 AMU, 1 atomic mass unit, as 1/12 of the mass of an atom of carbon-12. Here I have the mole as the amount that is contained in exactly 12 grams of carbon-12. Because both of the mole and the AMU are expressed as relative to the carbon-12, they can be related to each other. And this is how we can relate them. We can say that we can convert the 1 atom, which we know it's 1 atomic mass unit, to the 1 mole of an atom, which is the molar mass of that particular atom. 1 atom gives me the atomic mass, 1 mole gives me the molar mass of that particular atom. These two numbers will be the same, and they're equal to the number that you find underneath the element in the periodic table. But if we're looking at just in terms of 1 atom, it will give me the atomic mass unit. If we look at the same number but in 1 mole, because it's just 1 mole of the atom, it gives me the molar mass. The difference between 1 atomic unit, mass unit, and a molar mass is that there are 6.022 times 10 to the 23rd more atoms in the molar mass than in the atomic mass unit. For the 1 atom, we look at the mass of the 1 atom, and that gives me the atomic mass. When I look at the mole of the atom, it gives me the mass of 6.022 times 10 to the 23rd atoms. So the mass of that many atoms gives me the molar mass, the mass of 1 mole. 1 atom gives me the atomic mass of that particular atom. But these are the same number, they're just different in what they're measuring. The 1 atom, the atomic mass measures the mass of 1 atom. The molar mass measures 1 mole of the atom, or 6.02, the mass of 6.022 times 10 to the 23rd atoms. And that's the difference. This is small scale, this is really large scale. So if I were to look at the same molecule of H2S, I would say for 1 molecule, I have 1 sulfur and 2 hydrogens for 1 molecule of H2S. If I have 2 molecules of H2S, I would have 2 atoms of sulfur and 4 atoms of hydrogen because I would multiply by 2, 2 times 2. Now if I have 6 molecules of H2S, I would have 6 sulfur atoms and 12 hydrogen atoms altogether because I have twice as many hydrogens as I do sulfurs. And I have the same number of sulfurs as I do molecules. If I have 1,000 molecules of sulfur, I would have or hydrogen sulfate. I would have 1,000 atoms of sulfur and 2,000 atoms of hydrogen. What if I have 6.022 times 10 to the 23rd molecules of H2S? That means I have 6.022 times 10 to the 23rd sulfur atoms and 2 times 6.022 times 10 to the 23rd hydrogen atoms. 6.022 times 10 to the 23rd molecules is 1 mole, is the same as 1 mole of H2S. So if I have 1 mole of H2S, that means I also have 1 mole of sulfur because the ratio is the same, but I have 2 moles of hydrogen because I have twice as many hydrogens as I have 1 molecule. Therefore, if I'm now talking about moles, which is nothing but 6.022 times 10 to the 23rd, that gives me 1 mole of sulfur and 2 moles of hydrogens because 1 molecule has 1 sulfur, so it's a 1-to-1 ratio. 1 molecule has 2 hydrogens, so it's a 1-to-2 ratio. So I'll have twice as many hydrogens per every molecule. Now, I have worked out this example, how to calculate this in a video, so you can watch this. But always remember that 1 mole is the same as 6.022 times 10 to the 23rd atoms, molecules, ions, eggs, etc. So if I have 1 atom of calcium and I look underneath the symbol of calcium in the periodic table, you'll see that it has 40.08. So 1 atom itself weighs 40.08 AMUs, atomic mass units. But if I'm looking at 1 mole of calcium, which is 6.022 times 10 to the 23rd atoms of calcium, right? I have 1 mole of calcium, which is 6.022 times 10 to the 23rd atoms. If I look at the mass of 1 mole of calcium, that will equal the same amount in number as my AMUs, but it's now in grams because I'm looking at the mass of 6.022 times 10 to the 23rd atoms instead of 1 atom by itself. So these are the same number, but they just differ in the scale. This is atomic mass units, which is very small. This is in grams, which is very large. So if I told you, and we will now, from now on, we will really just deal with moles and not atoms because we really we can't weigh 1 atom. A single atom is just not possible for us. So what we're going to deal with is the mole. And to figure out how much a mole of any element weighs, you just look underneath the symbol for each element, and you will find where we talked about the atomic mass, it's the same as the molar mass. So if I look at the element of calcium in the periodic table, it's element 20, you will find that 1 mole of calcium weighs 40.08. The 40.08 underneath the element of calcium can stand for AMUs, but it can also stand for grams when I'm dealing with a whole mole, or 6.022 times 10 to the 23rd atoms of calcium. If I'm dealing with 1 atom, it's just AMUs. If I'm dealing with 1 mole, which is this many, the mass of this many atoms is now in grams. And it's feasible for us because I can weigh this much in a laboratory scale. Now, how do I calculate the mass of a compound? So if I have 1 molecule of calcium chloride, it will weigh about 110.98 AMUs. However, if I have 1 mole of it, I have 6.022 times 10 to the 23rd molecules of calcium chloride. I have the same number of calcium atoms because it's a 1-to-1 ratio. For every molecule of calcium chloride, I have 1 calcium and 2 chloride. So I have 6.022 times 10 to the 23rd atoms of calcium, but I have double the atoms of chlorine, which is 1.204 times 10 to the 24th atoms of chlorine, because I have double this number. 1 mole of calcium chloride, I have 1 mole of calcium and 2 moles of chloride. If I were to look at the mass of calcium chloride of 1 mole, or the mass of 6.022 times 10 to the 23rd molecules of calcium chloride, I would find that it weighed this much. And I've made this video to show you how to calculate this number when you have two different atoms that make up the molecule. This is true for any, we can follow this method to calculate the mass of any compound. And we will do a bunch of these problems in class, but I wanted to just show you how to do this example. And then the rest of the slides have problems where we have to use the molar mass, which is the mass in grams of 1 mole of a substance. This can be used as a conversion factor. So if you want to convert from an amount in grams to moles, I can use this as a conversion factor. Or if I have moles and I want to convert to grams, I can use this equation here, this equality, to convert back and forth. And these examples will show you how to. And once again, I've made videos to show you how to do all of these. So watch these, and this one as well, which is this problem goes from the grams to moles of aluminum bromide, whereas this problem has you going from moles to grams, so in the opposite direction. You use a similar method, we just going in a different direction. And I have shown you how to do both of these problems. If you have any questions, please ask, but we will be doing many of these problems in class. And then the last problem is similar to the other two. However, we have one more step here because we have to calculate the mass from a volume and a density. And once again, I've shown you how to do that as well. And we will be doing a lot of these problems, how to convert from moles to grams and grams to moles, how to calculate the molar mass of compounds in class. So if you have questions, please don't hesitate to ask. And this concludes the lecture for Chapter 2.